Hello, everyone. Well, I'm Luca De Paola, the team leader of Team Isaac. And thank you for being here at 7 p.m. of a Thursday. Today, we will talk about mechanical design. But first, I would like to introduce you a little bit to the team, what we do, and who we are. So we are a student team of Politecnico di Torino. Our name is derived from the sci-fi writer Isaac Asimov, not from Isaac Newton, as sometimes people say. We have been a student team, and we deal with mobile service robotics. So essentially, the robotics is not in industry. And we have 35 active members in different areas, from mechanics to software, etc. Yeah, we were talking about service robotics, which is helping humans in doing work in general. But in particular, we deal with search and rescue robotics. So we try to help and maybe replace humans in dangerous operations, for example, exploration, research after, for example, a catastrophic outcome like an earthquake, etc. Our prototype is this one. This is a very real picture, and is the concept behind our robot. We have designed a snake-like robot, so it has a modular design, a reduced frontal area, but being like a snake, it can lift some of the modules and overcome obstacles which are bigger than the robot itself. And we have done two main prototypes. This was the first one to see if this kind of robot was actually able to work. And this was the first prototype. We can see that it can do some steps, go beyond small obstacles, but it had many flaws. For example, the large area between the tracks made it stop on small obstacles in general. So we went to the second prototype, which is this one, which has a smaller frontal area. It has an actual arm and not just a camera at the front. And it's also more powerful in general. And we can see it here competing at the RoboCup Rescue and actually doing something which is difficult for robotics in general because it is a competition. And yeah, now that after this short introduction, let's talk about, let's say, the mechanical design, what you're here for. And I will leave the floor to Vittorio Giulimondi, who is the head of the mechanical department of the team. And he has 2 years of experience, and we will try to explain something about mechanics.
Okay. So hello everyone. The idea behind this class was to help our new members, especially in the mechanics area, to understand a few basic concepts about working in a team in general and about designing for robotics, and also with a particular look for the 3D printing section. All right. So. Why are we actually doing this today? Okay, as we know, Politecnico lectures there is a lot of theory in them, much less practice. And so once we get out of those lectures, we usually do not know how to solve anything, okay? So we encounter a task which might be actually difficult in the real world during your working experience in the future, and you will see that you actually do not know what to do. And that is perfectly normal because no one has ever told you how to do this. One example that we always do is that once someone new comes into our team and start designing parts, is that they never take into account about the electronics part. And the fact is that as mechanics, we do not care about electronics most of the time, but it's actually essential because without electronics, our robot will just not move. And so what I want you to get from this class today is for sure some tricks about SolidWorks that we will see. And maybe they have not shown you in the only one course that you do as mechanical engineer or industrial engineer in general. I also want to show you what is the actually workflow that anyone kind of has to follow to come from an idea to an actual product that you can print and use. And I want to leave you also with this quote by myself that there is actually no Nobel Prize for mechanics. What does this mean? Is that most of the times, I know it's great, we have a lot of great ideas that looks incredible, but they are extremely complicated. And the main problem is that when we have this kind of ideas, it's actually really hard to get a prototype because they are complicated. It takes maybe years to complete something like that, even if it's the coolest things on earth. So what I want to get you for today is to do something maybe a little bit simpler that is working, to have an actual prototype working first. And then we can actually upgrade it to some incredibly complex that will grant you no Nobel Prize because there is none. Okay, why should you actually believe us? What we are going to say to you is just because we're just students. I was just a student 2 years ago. I entered the team and I made a lot of mistakes, a lot. The leaders before me just corrected them and guided me to solve many of my designing problems. And what I want to say to you is to give you like a little shortcut, okay? So to just have a look and solve some issues that might come so that maybe in a few years, few months, whatever, you're going to think about today and say, okay, maybe they told us something like this and probably it's going to work and it's going to save me a lot of time. And I hope that someone else did this in the past, but there was none. Okay, so yes, this is the idea for today. So how do we go from a task that has been assigned? We usually assign them every week to each of the members of any area, particularly in mechanical area. So how do I go from a task to something that works, okay? What is in that cloud? We don't know. Usually not actually in the mechanical area, but maybe in some others, a little bit more. But there is the, it tends to be something like this, okay? And I mean, it's perfect to get maybe first design, first ideas. But the photo that you can see on the right is something that happened to me because I was doing some communication task. I had to design a little flyer, and I wanted to remove the, what was behind the robot inside the photo. And I told ChatGPT to do, even if there are a lot of tools online that can do it in 5 seconds, but I just wanted to see what it has done. And after a few hours, it generated me this picture of the robot, which is kind of pretty different from the real one. So fortunately, ChatGPT will not steal my job yet. So what are we going to do actually today? So first of all, I'm going to give first a very short tutorial about Google Drive Sync. This is something that we use inside the team, so it's taught for the team members, but also every other one of you can have a look at it. It's extremely useful, especially when using SolidWorks. We will discuss it later. But then we will also talk about this, the task simulation. As you may have seen on the mail, we will design a simplified version of our actual end effector, and we will see all the steps that we have to follow to complete the task. And then in the end, we also are going to have a little 3D printing overview, especially regarding tolerances, which is something that is not taught anywhere on the standard courses or lectures of Politecnico. So we can have a look at it too. Oh yeah, this is the, the workflow. So about the Google Drive Sync, why do we want it? Because when you're working on SolidWorks, maybe it has happened to you, but if you have an assembly is composed of multiple parts. And what happens is, if I just send to another member of the team my assembly without the parts, it will open the assembly, and SolidWorks will say, I don't find any of those parts, and will open just a blank screen. So the fact is that I can either send them the assembly with all the parts, and just consider that our main assembly with the robot contains something about 2,000 parts, something like that. So it might be pretty heavy to send. or we can use Google Drive. The fact is that to use Google Drive and access it on SolidWorks, you need to have synced on your PC, which is something extremely useful and fast to do. So I will give you 5 minutes and tell you just how to do it. The idea is that you just have to download the drive for desktop, and then you log in, and you do not care about the configurations yet. If you want to configure things, that's up to you. Then the fact is that you probably will have like a shared folder for the team or the working space where you're working. And then you need just to upload it on your drive, as you can see on the photo here. And once you have also downloaded the Google Drive on your desktop, you will just have it here, outside your disk, and you can just add it to your quick start so that you have it extremely easy for access, like I have it here. Okay, so this is just something that might be useful for you, and maybe also for today. So let's get into what we want to do today. Task simulation. As I said, every week we actually give tasks to the members, and this is something that happened last week. So it was something like this. We have a competition in 1 month. We need a very fast-to-do end effector to test the arm. We thought about the Boston Dynamics end effector. We will see it later. It just has 2 clamps to take objects and support for the real-sense camera, which is our main camera for the robot. And then we also need to attach the end effector to the previous motor on the arm so that we can move it around. So once a task is assigned, and maybe it is written somewhere, we also need to understand what we want to look at first, okay? So, and especially to look at what we still do not know. So let's consider that I do not know anything about the Boston Dynamics end effector, the real sense camera, and what motors are we using. So where do I find them? So it's pretty easy. I can just search the end effector. And for the other parts that are using in the robot, maybe there is something on the Google Drive. Or again, I can just search them on Google. I can also find, if it's pretty famous, we can find it also for a CAD model of it. So let's see, the Boston Dynamics gripper. Why did we choose this? Because it's actually extremely easy. It has a motor in the center part, and then it has 2 clamps. One that is fixed at the bottom, and the other one that is moving. So just the motor is moving the upper clamp, and it's just working. It consists of 3 parts. It's extremely easy. And actually, we were designing a much more complex end effector by that time. And it would have taken much more time to complete. And in 1 month, we had the competition. So we thought, OK, let's do something much easier. This took like 1 afternoon to do, another afternoon to print, and it was ready. So now, how do we will attach it to the arm? We just need to take into consideration that we have also a motor at the end of our arm. So this is just for later to understand how am I going to attach, because of course, if I do a perfect end effector and I don't know how to attach it to the arm, then I have an end effector that grips things on the ground, which is okay. Now. I have uploaded some files also for you to have a look if you want to work with me with the development of the end effector. For the team members, you can find it on the Google Drive, this path. And for the non-members, you can scan the QR code. With this, you will have a shared folder on Drive. And in this way, you can just upload it on your actual Drive and open it. È scaduto. We will see, okay, the QR code is not available. These free QR codes. Okay, maybe we are going to fix it. Once it's fixed, I will give you again the QR code. But do not worry, I will show you everything. These files just contain the CAD models of the motors and the real sense. So you can see it on my PC too. Oh, please, for the team members, just use the drive synchronization for once, so that I do not have to repeat you all weeks, okay? No, okay, so now, what are we actually going to do now? Are we going to make the 3D model to start modeling? Well, of course not. We still do not know anything. So the first things that we need to go and watch is the models of the motors to understand what actually are they. So let's see, I have it here already open. This is our motor. As we can see, we have this axis of rotation here. It's going to rotate. I can see here that in these holes I can just put screws so that I can make something that attached to it somehow. And how can I attach the motor to the end effector? Well, I see there are other holes here where I can put screws and etc. Especially for the motor, it's actually pretty common to find something like this, which is even easier to use, okay? I also have it here printed. Okay, so now we have seen the motor. Let's see, the other part was the real sense. Okay, here we have our camera. It's pretty cool. How can I attach to it? Well, I have a big hole here and also another one here where I can put my screws. So maybe I can use something like this. I don't know, but just to have a quick look at what we need to use. This is kind of essential. Okay, so now we have seen these parts. What do? We start making the designs? Well, no, because we still do not know what to design. So what I suggest is that once you have a task assigned and you have seen the parts that you need, is that you first do a first sketch. I know this might seem something stupid because you can say, I have everything in mind, and maybe you're right, you have everything. But if you do not do a sketch, you do not think about things that I will ask you later. Okay, so let's do something. Let's consider our motor. Okay, something like this, with our axis of rotation here. Where here there are all the holes, okay, that we have seen later. Okay, so now I need to make the fixed part of the clamp and the moving part. Where can I fix it? Okay, I've seen I have multiple holes here in these parts, so maybe I can put the fixed clamp on the opposite side where I have my axis of rotation. So maybe I can do something like this, very similar to the one of the Boston Dynamics. And then I can do something that attaches to this other one. So I will do, not very good at drawing, but something like this, okay? I don't know. Okay, and then here we attach somehow, but we will see how. Okay, so now these parts are done. I need to still attach it to our motor, to the robot. So I need, and also to put the real sense there. So I can think about a way, where can I put my camera? I can put it here. Maybe I can put it here. I can put it on the side. It's pretty big, so maybe on the side it's not ideal. We'll try and put it just on top of it. So we need to design something that holds it. Let's make, for example, something like this. I don't know. And this will hold my real sense that will be placed here. Where do I want to place it? Maybe a little bit nearer to the front, a little bit in the back. We can discuss it, of course. If I put it a little bit too much on the front, then when this goes up, I can hit my camera. And given that it costs, okay, there is this is again available. I will put it, so if you want to. Okay. Okay, so I can put it a little bit more on the front, but then my clamp will probably hit my camera, and consider that the real sense costs something like 400 euros, 500, something like that. It's not ideal. I can put it more in the back, but then maybe if you consider also that the camera has a field of view, so I don't know how much it is, but let's consider, I know, 90 degrees, something like that. So I cannot see things here. And if I put it here in the back, then I will have a lot of my view will just be this blank space, and I will not see what I have in front of me, okay? But this is something that we can then check it out during the design by making the part modifiable later. So now, okay, we have done the real sense. We need to find a way to attach it. We have seen that there was another motor here that was just something like this, okay, which had, like, I don't remember, but something like this, an axis over here that then attaches to something else. So I can just extend this part as I've done and maybe attach it here with a few screws. Okay. What is, in your opinion, a problem with this design? Okay, I will also, have you all seen, took the QR code? I think, is there someone? Okay. So I will give you also, okay, this. Okay. I actually forgot to mention before, so maybe it's a little bit harder for you to guess, but have a look at this. Think also about what I've said before about mechanics, not thinking about electronics problems. Any suggestion also from the members? Maybe if I do something like this. No, it's something like this. Something comes to mind, which will be, I don't know if you, this part here, if you see my mouse. What are those? I forgot to mention, but those are the pins for the cables, all right? So the problem is that if we do something like this, then I have to put my cable inside. And I mean, maybe it will fit because, you know, I can bend a little bit the cable. But for the electronics area, it will be just hell just to make some tests, put the cable in, put it out again, because your finger will just be too big for doing something like that. So what is the solution? I can just place it a little bit farther away. So I just do something like this. I do something of this kind again. So now I have here my pins, but the cable can just go in and get out easier. So this is something that you need to take into account, because if you do your design, it's perfect, at least you think it's perfect, then you present it to the other area, to the electronics area, and to work on it. And if you're actually working inside a company, they will just tell you, you need to change it, because we cannot work on it. If you're working inside a team, they will just not work on it, because they don't like to work on it, and you will not have an end effector. This is the long story short. So we need to have a look also for what other areas might think of. Okay, so I think that for our first sketch, that is all. We can actually start modeling. So let's start with the, oh, by the way, I wanted just to have a little spoiler about this is the model for our actual end effector that we have. That, as you can see, it's pretty simple, but it's functioning. It has a little bit more cameras, but we will do a simplified version of it today. So, okay, let's start with the modeling. So, I mean, I hope every one of you has done the course for drawing during your lecture. And so let's start. I actually like to something like this. Let's start with a sketch. One of the things that I see most when I see other people doing sketches and parts is that they divide the part in a lot of sketches and a lot of extrusion cuts, whatever. The only problem about doing something like that, it is maybe easier at first, but then when you want to modify in the end the part, it is extremely difficult to find the exact sketch that you need to modify. So we will try to make just one sketch that contains everything, so that then we can then modify it. And we'll also discuss about the equations a little bit later. So let's see the motor. How can we fix it? We have seen that here there are those screws that I can put inside, and actually, this is something that you might not know, but these parts can be removed so that we have just this shape that you see here. This shape here, where we can actually fix the motor, put the screw inside, and then the motor will be fixed. At least, the clamp will be fixed to the motor. So let's start with something like this. So first, we need the actually clamp. So we'll do something like this. What dimension do we choose? It's actually pretty hard to guess dimensions first, but we can see now it is a little bit easier because we have the motor, so we can see that this is 28 millimeters of width. So, but I understand that having a guess about the dimension at first, it is hard, so it is something about a sensibility that you gain by doing a lot of parts, and it takes a little bit of time, but you can first try. So and then you can also change it later. So let's do something that was 28, maybe 3 times 75, something like this. Okay. What width? Something. Yeah. A little bit aligned to the sketch. Yes. Okay. Now this is easy. Let's start with doing the holder, actually, of the motor, the inside part. So we are actually going to do something, I don't know, like this. Okay. How are we going to do? Let's see from the motor. So actually, what is this, the dimension of this? Okay. How do I get dimensions from SolidWorks? Maybe you have seen it during the course, maybe not. It's actually really easy. Either you click on things and you see the length, or you use this tool from Evaluate Measure, which is actually extremely useful because then you just click things and it will just measure it for you. Especially if you just click on these X, Y, and Z, it will give you all the coordinates distances. So it's actually extremely useful. I see there a normal distance of 6.5, so it has to be, this line has to be at least of 6.5. Let's do it, I don't know, 7.5, a little bit more, yeah. What is this length? Again, let's use the measuring tool, or we can actually also use this. We have seen it, 28.5. Okay. No, it's not. Okay. So 28.5. Okay, right now I'm not considering anything about tolerances. We will discuss it later because tolerances change if you're doing a piece out of metal or you are 3D printing it, but we will discuss it later. So let's now consider these measurements. And now we need to make the holder for this part. Okay, so we actually need to kind of copy all of this. So let's see, for now, this is a little bit easier. So here I see that this is just a radius of 3.25. Where is it placed, actually? Where do I see it? Okay, here I see the place for the uses. 22 from the center. So I just need to make the holes. Okay. And then I will also make this part. Okay. So how much is the hole? This is an M2.5 screw, so let's do 2.5. Okay, and then here this was 3.5 radius, I don't remember, let's get it here. Yeah, it was 3.25, so this must be something about 6.5. All right, and these two. Okay. So now this has to be centered. Okay. So how can I center this hole? Just I put a line in the center of my square, and I click on it. I click on it, and I make coincident, right? And then how do I fix it also on this side? I can both make put a dimension, or I do the same thing here. Okay. Now, I have to make the same thing on the other circle. I could both make maybe a mirror, okay, of the sketch, or I can also use some relations and something that is called an equation. So let's see about it. So first, I want to have the same center of it. So let's do here. If I put it horizontal, it will be on the same line. All right. If I want a 22 dimensioning here, 22, all right. And then also this. How much will it be? It will be the same as the other. So instead of putting 2.5, I can put equal, and then click on this quote. So in this case, if I want to change it, put it like 3. Then it will just go to 3. 2.5, go back to 2.5. So in this way, it is much easier to change the design of this clamp. Also later for tolerances. So now, what is the difference here? Yeah, we have this little fillet here. So we need to make the same thing. As you have seen, is 3.5, 3.25. So how can I do it? I can both make a circle on it of 2.5, or I can use this other function, which is extremely useful, I think, which is this fillet function. I don't know why it does not take it, but let's make 3.25. Okay, a segment, okay. Problem? No. Oh, what? Oh, yeah, right, because this is not placed. So let's just do something like this. That was something. 3.25, okay. I love SolidWorks. Okay. Again, here I can use the function. Okay, this thing about function is something that is actually extremely used in a lot of cases because it can be upgraded to something much more complex. Just consider that, for example, it can be possible to have a text file outside of the SolidWorks, and then you can modify the values inside the text file, and then all of the dimensions on your sketch, which are related to the dimension of the text file, will change accordingly. So it is something that is complex. It takes a little bit of time to do, so we will not see it today, but can be extremely useful for us. Now, let's finish this. Just let's use a mirror. So we need to first do something like this. Where is it? Here it is. Okay, so let's mirror it here, here, and here. Of this, right? Over defined. Why? This something? Oh, because I'm defining 2 times this. No? Where is it already defined? Oh, I'm defining this 2 times. Okay. Okay. Okay, what I want to always get when I finish a sketch is this, what is saying here, that is fully defined. Because once a sketch is fully defined, of course, I cannot move anything about if I touch things. Otherwise, it will just change its dimension. And once it's fully defined, it means that you actually finished your work on the sketch. And you can go to the, to actually go in and extrude it. So let's do the extrusion. As we say, this will just hold the old motor on the side, and we'll have something which is actually mirrored on the other side. So let's think about it when we do it. But okay, so let's make this extrusion. How much will I do it? I don't remember how much was the motor with it. So this was, okay, this is 34. So I don't know. Let's start with 40, maybe. Okay, something like this. Let's make a mid-plane. So, well, this open. Okay, it wants me to select everything. Okay. Okay, I have my block from just one sketch. But now I do not have to do many more sketches because I have everything I need here. So I just go from the sketch. What do we want to do? We want to make the cut, okay, to place the motor inside. So let's go from this sketch and make the cut. Again, I put this plate. So how much is it, the motor again? It is 34, so I have 17 from one side and 17 from the other. So I have this 17. And also on the other direction, I have this 17. All right. So what am I going to select? Just the parts that actually I want to cut. Okay, maybe, yeah. Okay. Oh, maybe here I actually can avoid extruding these parts, given that are the holes and I don't need it. Right. Okay, so now I have my holder for the motor. I just need to add these little pieces. Let's take it from here. That I am actually going to eliminate to give the motor a little bit more of the clamp a little bit more structure with the motor, so I can fix them together better. So removing them, I have to create them on this part again. So again, I go from my same sketch as before. I go to extrude, and I just select, let's do, here I change because I want to extrude them from another face. So I change. I take this surface, I make a blind one, okay, from the other side, and I select the parts that I'm interested in. So this and this. Now, how much is it? I don't remember, but here it is written. It's 2.8. So let's see, 2.8. Okay. So I have it here. Now, it is the exact same thing on the other side. I can just mirror this time of function. Just consider that to mirror a function, you do not need a line, but you need a whole plane. So let's go to the mirroring, which is here on the linear pattern. So I have the mirror face, which is this. It's not selecting it. Apro? Nella tendina. Fixed clamp. Aspetta, non lo vedo. Quale dici? No? No, sì, ma perché non lo va? Ok, sì. Thanks for the help. Okay, now we can just select the parts and mirror it. Easy. Easy. Not mirroring it. Partial view, full preview. Geometry. Why not? Any idea? makes sense. Okay, I will just copy all the faces. If you can never use SolidWorks in your life, in fact, in a company you will not use it, but but why is it not? Il piano. Oh, Dio. I have another idea. Cancel. Okay. I didn't want to do this, but they are actually forcing me to. So let's get again the sketch, extrude it, and okay. Let's see. Okay. Okay, now we have our part. So we can, what time is it? We can move on and do another part, so maybe it's better if we first do an assembly. So let's make a new one, an assembly, to see if everything is working. So I take the fixed clamp in here. Okay, and I also need my motor. So I insert a new component, and I need this. All right, yes. Let's remove these parts. I don't care. Okay, so let's make some mates very fast to see if everything is working right. And it looks like it is. Okay. So we have what we want to see is that the holes are actually centered, because most of the times we just click something and we make some holes that are a little bit placed off. But now everything is working. Of course, there are no tolerances, so this is exactly perfectly fitting the motor. But again, we will discuss it later with the printing files. Now, we do not have a lot of time, so I will skip the upper clamp, the moving part, but it's actually pretty easy. As you can see, if you have done this, it's actually easier, because it's something like this, so you just need to make the holes here to put the screws inside. So it's actually kind of the same, even easier, I think. What I want to do is the support for the real sense. Then maybe it is easier, but it is actually pretty interesting for tolerances and for another feature, which is actually the configurations in SolidWorks, which is pretty cool. So again, let's do our sketch. Okay, let's start with, I need to remember the dimensions again. So this is 28.5 here. And on this other side it is 34, okay. So, yes, it's okay. So we'll just get, I mean, as we have seen it before, it would be something like this. Okay, this would be something of it. Let's start adding the dimensions to it. 28.4. On this other side, it was 34. Okay. Again, here it goes down for at least the height of the motor, let's say. So it's 46.5. Okay. Now this is, let's make them collinear. In this way, I don't have to make more dimensionings. So now, maybe I don't know what else do I need to dimension. I just click the parts in blue, I move them, and so I understand what is the problem. So let's do with the dimension. What actually is missing here is the thickness. Now, thickness is something, again, that is really hard to guess at first, especially when you are not very familiar with 3D printing, because you're thinking that 3D printing, you print plastic. So plastic is something that has not a lot of strength, and which is true, but it depends. What are we going to use this part for? They're going to fix two motors together. How much strength am I thinking they will get? Not extremely much, even because if you need to make a component that has to be really strong, you do not make it out of plastic, you make it out of metal. So everything will change. So how much will you do it? I mean, I see people that do something about like 50 millimeters of thickness that might not look much, but this is kind of something like maybe it's 1.5 centimeters, something like this, and I cannot break it really easily, and it's out of plastic, okay? So for something like this, I will put something like 5 millimeters. It's pretty fine. It's not much, so if I apply a lot of force to it, I will break it, but I hope I will not. Okay, what is missing here that it's not defined? Here, no? The thickness is here. Thickness is here. You're seeing something that's not defined. This part is not defined, yes. Yeah, of course, yeah. That is exactly what I want him to do. So let's put it vertical, okay. So now this is fully defined. I can move on with the extrusion. How much do I want it to extrude? Well, let's see. It depends on how much the motor length. So here I can see this is, where is it placed? Here, 34, right? We've seen it before. So let's extrude it again. Let's put a mid-plane, 34. Maybe we'll do it a little bit less later. Okay, we have something like this. Now we can do the holes, but first I wanted to have you look at something. Did I forget something to add here? Yeah, probably. If you also watch the sketch, it's a yes. I forgot to put the holder for the real sense, which is the reason why I'm doing this. The reason why I didn't do on the exact same sketch I could have done it, but it's because I want to introduce something which is the configuration system in SolidWorks, which is actually extremely useful because it gets you to turn on only some functions instead of others. Let's see what I'm meaning by it. So let's do the real sense holder. So we have seen we have these two holes, okay, and we want something like this, okay, so that the real sense is pointing towards the clamp. So the fact is, where am I going to put it? We were discussing it before, and we still do not know it. So I will put it here in the front, on the back, in the middle. I do not know. So first, let's see where the plane is. So we still, okay. But we need a sketch, okay? It's not just a function that we can make it as large as we want. We need a sketch, and a sketch needs a plane. So we need first to define a plane, so we can define a new plane by defining the geometry. And we will make it parallel to this other one. It's lagging, not. Let's put it, I don't know, here seems fine. Okay. So let's start designing it. So with a sketch, I start doing it. Oh, it's on the back, well, it's fine. And so how do I do it? Something like this, I don't know. Okay, now the dimensions, I don't remember absolutely anything. Let's see, so I get to the evaluate, measure. Here it tells me how much it is, but okay. So this is 45 millimeters, and the diameter for the screw will be, here it says it is. It doesn't say, oh yeah, 1 point, no, okay. 1.12, so it's an M2.5. So let's go to our sketch again. It was 45, so I need to make it a little bit larger. I don't know, 55, something like this. Okay, then I will center it back. And So let's center it. So we want something like this. We just put something. Oh yeah, I didn't center this too. Where is it? Okay. Oh, is it? Center? Coincidence? Oh, no, right. Okay, now I can put it again the mirror. Okay, so let's do this fast because it's a little bit boring even for me. So this is something like this. Again, horizontal. My PC is lagging, not. Whoa. It has a little bit of lag. Yeah. Come on, you can do it. I know it is. Oh, I was, yeah. Yeah. So let's finish defining this sketch again. So how much of height do I want? I don't know. Yeah, 10 will be fine. So the thickness of this, 15, seems reasonable. Okay, fully defined. Let's get to the extrusion. Oh no, wait, I'm forgetting the holes, right. So I get here to the sketch. Again, I'm already sketching, yes, that's right. So let's put the holes. Okay, so let's do it again. 2.5. This is 2. Equal to this other one. They will be on the same line, and again on the also the distance will be fixed. Yeah, coincident. And so also to this other one. Okay. So this was 45, if I'm not mistaken. So this means that if we want to make a, oh, I can do it like this without a line. Is 22.5. Right. Okay, fully defined. Let's go. Now, thickness of this, well, it just needs to hold the camera, which I know how much it weighs, 100 grams maybe. So I will do 5, but it's still a lot. We can even do less. It actually depends on the type of screws that we are having, because you just need to consider that inside the camera, here there is some depth, right? Let's see, we can measure like this. It's 1.6 millimeters. So it means that, for example, in our lab, we have these screws that are M2.5, I mean, I think it's 8 millimeters. So it means that we have to make a thickness of something about 1.8 minus 1.6, like 7 millimeters, something like that. No, sorry, 6 millimeters, something like that. 7 millimeters. I mean, I don't know how to count things. I make ChatGPT do stuff. I don't know. Okay, but anyway, so yeah, it's pretty thick. So we can also think about something much better later. But okay, so the fact is that, as we can see now, if I do not like the place, I can just go to this plane. Okay, edit feature, and I can bring it a little bit more on the front, maybe like this, so that I have the real sense a little bit more nearer. So the idea is that when you design something, you want to make it as much modifiable as possible. It must be really easy to modify, not just by you, but you need to consider that maybe someone else will work on that file, and it has to be easy to work on. Okay, this is the general idea. Now, let's go to the tolerances, which are much more interesting than this. Let's get to the PowerPoint. Okay, has any of you any experience on 3D printing? Kind of? Yeah, someone? Okay. How does 3D printing work in general? As you can see in the video, it starts from the bottom, then it goes to the top. It deposits layers of filaments, and now this is like maybe 50 there of velocity, because for something like that, it would take 5 hours to print, maybe a little 3. But the fact is that, so I want to print my cube here. So my printer will start to deposit layer by layer, all right, on the top. Not only on this, but here I'm looking at, this is, I don't know, this is the z-axis, okay? But if I look at the plane, x, y, so I'm looking it from the top, I will have the same thing, right? So I have my, I know, it's not a cube, it's a parallelepipedo, no. And you will just have the same thing here. The fact is that, just consider something like this. My printer will start to print, will continue, and then we'll arrive at something like this, all right? What does it do? It stops, or it goes one more? Non si vede. So also for the registration, what I'm doing is that I have something like this. I will start printing it with my filament. I arrive here, and I have all of this part that I don't know what to do. Now, what will the printer do? We'll fill it this way, so that it will have actually an extra part here, or layer. So I will have a tolerance here, more material that I actually needed, or we'll just leave it blank, so I will have less. Now, this we actually, well, yeah, you can know it by making some tests, but it depends on how the printer was actually coded, okay? Depends on the software area of your printer. So the fact is that we need to take into account. Now, consider that each printer has a nozzle size, which is this part here, which is actually the part that you see here depositing also on this. This is actually the height of the layer, but it has also another kind of dimension. But it just deposits filaments of a width of, for example, our printer goes from 0.2 to 0.4 millimeters, which is low, but is not actually that much low if you think about it. So for example, there are some problems. Let's also look at the photo. This is a circle. This is one of the main problems when designing something that has to be 3D printer, especially for holes. Because if I have a circle like here, this is a hole, okay? So my printer will start, okay, we'll do it here, no problem. But then it comes here. Where do I stop? Okay, do I stop here? Do I stop here at the center? Do I stop at the end? So I actually have something like this. I do not know, okay? I just have to test it because it depends on the printer. I can make some modification, but again, I will not have something perfect. Now, this is very low, okay? This is 0.2 millimeters. But still, if I want to have a perfect circle, I cannot have something like this, okay? It actually depends also if you are printing something in one side or the others. So I'll give you an example. This that we have right here is a hole tolerance tester, right? It's actually pretty useful and common when we want to print something in 3D. And this was printed horizontally, so meaning that that is the plate, and the printer went like this, okay? What is this useful for? Because here there is actually written all the diameters that were designed on the printer. So for example, if I want to I have this shaft, and I want to get a hole for this shaft without much interference or either play. So I just get it inside, and I try and see which one gets it. So let's see. I see here at this is 9.8 millimeters. It gets a little bit of interference. No, sorry, this was 9.6. This is 9.8. It goes through pretty smoothly. At 10, it's a little bit loose, kind of a lot loose. This was probably designed at, it was a 10 millimeter diameter. So if I design a hole with a 10 millimeter, it would just be too loose. But then, so I say, okay, I will design it 9.6, and then there is a lot of interference. If I want something right, I can do it for 9.8, right? So this is something, but this changes because if I print something vertically, so if I print this vertically, we have also another printer, I do not have it here, but that is printed vertically, the shape of the holes, and not only that, the actual diameter will change. So it means that maybe if I print something horizontally, 9.8 was right, but if I print it vertically, usually our printer, when it is printing vertically, it makes holes a little bit smaller. So maybe it is needed 10.2. So I don't know, I have to test it first. And usually, in fact, the very fortunate thing about 3D printers is that plastic is not expensive at all. So you can make tests and make a lot of mistakes, and it's not a problem. But again, we need to take that into consideration. But, so, for example, let's see in our designs, what do we need to change? Oh, and by the way, of course, also motors have tolerances because they are manufactured. But we assume that they are manufactured by a company in an industry, so they actually have kind of a tolerance, a zero tolerance. In respect to us, they do not have a 0.2 millimeters tolerance at all. They have much less tolerance, so you can actually assume them to be almost perfect. Otherwise, if you need to make something extremely precise with metal, where their tolerances can go much lower, you need to take that into account too. But for today is not the day. So let's see our parts. Okay, so for example, in this part, what are the parts that we need to consider for tolerances? Okay, so we have said that the printer might do things a little bit wider, a little bit smaller. So in our case, the printer tends to do things a little bit wider when it prints that because also the filament will lose a little bit when it will flat a little bit, so it will occupy a little bit more space. So let's consider that we have designed this, that will be exactly 34, right? Yeah, 34. But maybe it needs to be a little bit wider. Is that a problem? Well, no, because we just need to modify this a little bit. So this was 17. How much of tolerance do we want to put? I personally do I use the tolerance of the nozzle, okay? So for example, if I know the printer is printing with a tolerance of 0.4, the nozzle is 0.4 millimeters, I try and add this 0.4. But again, it just depends on the printer, you need to make some tests. But in this case, I will put like 17.2 and 17.2, which adds to 0.4, 17.2. Okay, now if I have defined well all my functions before, there will be no problem, no issues in changing things also on the sketches, right? Otherwise, if I've defined them poorly, it takes much more time to change things. So let's go, for example, to the sketch. Where would I want to define? I will not do it because we do not have much time, but what do I want to see? Consider that this part might be just a little bit bigger. So we can, let's do it, this takes nothing. So this, I want to put like 6.3, maybe, or 0.4. I don't want to increase it too much. This, let's do something like this, which is better. Okay, so I guess I gave these tolerances on this. Also on the holes, because you need to consider that from how a screw is designed. I'll do it here. But I have my hole, right? and I will print it. So let's consider that my printer does something like this. Okay, it will overlap it a little bit. So this will not be 2.5 millimeters. This will be a little bit less. Now this is exaggerated, but still. So if I have a screw, a 2.5, M2.5, this will just not get inside. Or better, it will get inside, but you will risk on ruining the hole, okay? Which is actually something that you might actually look for, because of course, if you have a screw, then on the other side, you need actually a nut, okay, to block the screw. But if you do not want to use a nut, because let's consider if I want to block something that weighs nothing, I can just use plastic. So I can just screw this inside the plastic, so I can maintain a 2.5 millimeter hole. Consider that the printer will just do maybe 2.3, so that then the screw will get inside and will fix itself without the need of a nut. But in our case, we want to go through smoothly, so let's change it to, I don't know, 2.8. It's not a problem to exaggerate even. Okay, so we dumped this. Now, I didn't change one of the tolerances that actually is pretty much considered, and if you've done the course here at Politecnico, at least for me it was kind of hell to understand those parts, is about the hole's position. Because in every course you learn that tolerances affect the hole's position. I have here 2 holes. They will not be on the same axis, they will not have the exact distance that I give them. This is something that, do I have to take this into account when I consider 3D printing? And the answer is no, because the printer has not a problem in tolerances on putting in the right place. It has much more on dimensions. So just consider that the tolerances of the hole will be just much bigger of wherever you will just adjust the tolerances for the position. So usually you just do not take into account by doing during 3D printing. Meanwhile, if you do it while designing a metal piece, you kind of have to make sure that those things are right. So also for the other piece, the same thing. Oh, we did not make the holes here yet, but also for the camera, I will have to change it, the holes. Or for where I'm going to put the motors inside here, if I were to making the holes on top, I need to consider that if I make this motor really close to the other's wall, like let's see on a part that's been done, like here, I need to consider that there must be a little space. Let's see if there is some. Yeah, really a tiny little space. It's not much, but it's the one that is needed so that when you just build everything up once you've printed it, it is actually working. Otherwise, you just need to print it again. And it's not a problem of plastic because, again, something like this costs maybe 30 cents, but it will take like 3 hours to print again, so you have to wait a little bit. This is actually kind of the end. Oh, I have this time. But okay, so the fact is now, how do you, we have 10 minutes still. I will show you what we have to do to print it actually. So, of course, when we save, let's see this part. When we save a part, we save it in a SolidWorks file, part or whatever program you used, but most 3D printers will not see this kind of file, so you will need to save it in another way. Let's see. Save as, yeah, I don't know. Okay, we need to, there are multiple files that can be saved for, either step files, but we usually use STL, which actually what it does, it creates kind of a mesh of the object, so that then in the 3D printer program, it can create the code for the 3D printer to follow. We will see it just now shortly. Okay, so let's save it. As you see, it has created that mesh. And let's go from here. We can open it. We have a Bambu Lab printer, which is actually pretty decent. Actually, the tolerance that I told you, 0.4 millimeters, is extremely low. Just consider that this is one of the best home printers, okay, that you can get. So it is slow. No. Okay, so we have something like this in here. Dio. Okay. So something like this. Okay, now, how are we going to print this part? The fact is that you need to take into consideration that the printer goes from the top to the bottom. I will show you again the video. I really like it. Here. It starts from the bottom and goes to the top. So if you have a roof, then you cannot print. Let's think about if we have a very large 3D printer, we want to print this room. Okay, impossible, but just consider something like this. We can print the walls easily if we print it like this. The stairs is not a problem, but the roof is a problem. We do not have anything to print on. We have just an empty space. So in this case, we can see that there is this problem, okay? We want to, this part is not on anything. Now, the filament has this kind of property. It can print something over an empty space, not much. It can bridge a little bit the two spaces. So for example, if I have something like this, if I want to print this part, for example, if this is not too much of a width, it will print it, no problem. So it will just go here and also on this other part, and then it will just go straight. It's not a problem. But if it is too much, it will not do it. What happens is that if we have a larger bridge, we can make supports, right? So, what actually is happening is that the printer or ourselves are creating more parts, like these little parts here, that will just attach to the actual object just in tiny spots, so that then it can print. When it goes here, it will just get on these tiny spots, and the printer will just continue, will not fail. And then when you actually want to take the piece out, you can just detach them very easily because they attach in a really small spot. Let's see, this should be actually, in this program, it's extremely easy. It's already implemented. So let's see, here it is. So with this button, I actually sliced the plate. So it means that it created it's called the G code. It's actually code for the printer to follow, which is the path that it has to follow. So you can see, let's remove this. Here is all the layers of the object. And here we can see that on this other side, this arrow is the nozzle. We will just print everything, and here is the code that it has to follow, just for one layer. And then it goes on to the other one, all on the top. So as we can see here, it created these three support that can hold this part. And the problem is, why are we doing actually this? It's much easier. We can just place it in this way, and it does not need any support at all, in this case. Now, are there some times where I want to print something in a different way, as it should be? Let's take, for example, this. This is a shaft. Here it is attached to the motor, a very similar one to the one that we've seen. It goes inside actually our arm that is needed to rotating. It will lift the arm. So it means that it takes really a lot of pressure. In fact, we are making them out of metal right now. But this first prototype was made out of plastic. Okay, why should I want to print it like this, or like this, or I don't know, also in any kind of way? It depends on the strength, because you need to consider that. Let's make a big rod. Okay, let's print a rod like this, okay, and a rod like this. So my printer will start printing, and we'll do all of it until the top. The fact is that it's placing one layer on top of the other. This means that if I apply a little bit of force here, I will just apply it on the layers, and this can probably break, okay? Because the layer will just deattach to one another. Meanwhile, if I print something like this, I have just one long line, a really big layer. So this means that if I try and apply forces on this side, I will not encounter two layers. I will encounter just one line of filament, which means that the structure, the rod, will be just much more durable. So for example, if I have a shaft like this, I imagine that it will just get this kind of pressure. Now, if I want to make it extremely durable, I have to print it like this. And this way, it will resist kind of a lot more. The only problem that printing like this will get you much higher tolerances on the circumference here, because it will just not print it like a circle. It will print it kind of, again, something like this. So it will not be a circle, it will be just a multi-polygon shape, okay? Which was the same one that we have seen here on here. This is the case. If I want to make something this extremely with a lot of strength, I will get a shape like this. So this means that I need to take into account when designing other things, which means that it is much harder to get it right because it's harder. Meanwhile, if I print it on this side, which this was printed, I will get a much smoother surface, but probably it will just break much easier. So it is kind of a trade-off that you need to do when designing these parts. And you also need to take into consideration, and when we design, for example, this part, where is it? I don't know, fine. This part is kind of hard to print because, I mean, I wouldn't know exactly how to place it on the plane to avoid using too much supports. I mean, you can always use support, you're just using more filament, you're just spending more time to print it. But again, you can also add a little bit of a base if it's not a problem. So for example, if I go here, I think about, I don't know, but it would take it in any way case. But if I want to have a space where to put it, what happened? No. What time is it? Oh, yeah. So, okay, I will not define it, but let's do something like this, okay. So I will get something like this, so you have a base, and then maybe there will be some supports here to hold this part, and a little bit of here to hold this part too. But again, I gave it a basis to actually print, because yeah, otherwise it would just probably fall on one of those sides, and not exactly. But again, for example, for this part, it will not take a lot of force on it. It will not have to be a lot of strength. So we actually do not care. If we design this part, well, it is really easy to print it. So let's print it right, okay? If we have something like this, we need to think a little bit more about what we want to do and the trade-off behind it. So this is it, then. You just go and you print it, and it's actually, for Bamblab, it's pretty easy. So I think, so I think that we are kind of finished now. I hope that you like this first introduction to this kind of mechanical design, especially for 3D printing. And oh yeah, the last slide, please, if you can, just a few minutes more, because we ask you to, oh yeah, you find here on the left our links, and there we would like you to give us a little bit of feedback about the class. So this was the first time that we were doing it, so we like a lot of feedback. And also, if you want to see something more about it, you can write it on it. Maybe there is a question. I don't know. Yeah, there is. So anyway, I hope that you kind of like it. I know some parts are a little bit boring, a little bit maybe easy for some of you, but this is an introduction. We just consider from you getting out of the drawing class of Politecnico the first year. And this is something that might seem not extremely important, but once you are in front of a task that you've never encountered, I don't know, the pressure is a little bit high, and you do not know what to do exactly. So thank you, and good evening to everybody.